Find somewhere comfortable. You don't need to follow any of this closely. You don't need to hold on to any particular idea or remember a single word of what's said tonight. Just let the sound of the voice arrive and let it drift past, the way a slow river carries leaves. We're in no hurry at all. Tonight we're going to travel somewhere very deep, not far away. In fact, as close as it is possible to get. We're going to look at the rules underneath everything. The hidden architecture that holds every atom in your body together, that keeps the stars burning, that makes light possible, that makes this moment, you, resting, breathing, warm in the dark, possible at all. There are 4 of these rules, just 4. And everything that has ever happened in the entire history of the universe, every collision, every chemical reaction, every heartbeat, every thought has been an expression of one or more of them. You don't need to grip that idea. You don't need to do anything with it. Just let it settle somewhere in the background, like a lamp left on in a distant room. We have a long, quiet journey ahead, and all you need to do is rest. For most of human history, the world appeared to be ruled by an overwhelming number of separate things. Fire behaved differently from water. The moon moved in ways that seemed to have nothing to do with a stone falling from a cliff. Lightning was one kind of event. The pull of a lodestone on iron was another kind entirely. The world seemed full of distinct, unrelated powers, each doing its own thing, each requiring its own explanation. The idea that all of this complexity might reduce to a small number of deep, hidden rules, that is a relatively recent thought, and it arrived not all at once, but in slow, patient steps spread across centuries. The first great step belonged to a man sitting, as the story goes, in an orchard. Whether the apple actually fell or not, the insight Isaac Newton arrived at in the 1680s was genuinely extraordinary. He looked at 2 things that no one had ever thought to connect: the way objects fall toward the ground here on Earth, and the way the moon moves in its long, curved path around the planet. These seemed like different problems. Newton's insight was that they are the same problem, that the same invisible pull drawing a stone downward is also the pull that keeps the moon from flying off into the dark in a straight line. The moon is, in a sense, always falling. It simply moves sideways fast enough that it keeps missing the Earth as it falls, tracing that slow circle. His law of universal gravitation, published in 1687, stated this with quiet precision. Every object with mass pulls on every other object with mass, across any distance, with the strength that depends on how massive the objects are and how far apart they sit. One rule: 2 apples, the moon, the planets, the sun, all governed by the same quiet equation. It was the first unification, the first time someone looked at the apparent variety of the world and said, these are not separate things. These are the same thing, wearing different clothes. The next great step came nearly 2 centuries later, and it was even stranger. By the early 19th century, scientists had spent decades studying electricity and magnetism as separate phenomena. Electricity made sparks and drove currents through wires. Magnetism made compass needles swing, and iron filings arranged themselves into beautiful curved patterns. They seemed entirely distinct. Then a series of experiments, by Hans Christian Ørsted in 1820, by Michael Faraday through the 1830s, by others, began to show something deeply odd. A wire carrying an electric current would deflect a compass needle. A moving magnet could push a current through a wire. The 2 phenomena were not just related, they were entangled. Each could produce the other. James Clerk Maxwell, a Scottish physicist working in the 1860s, gathered all of these observations and wove them into a single, unified mathematical framework. His equations, published in their final form in 1865, described electricity and magnetism, not as 2 forces, but as 2 aspects of one force, electromagnetism. A changing electric field produces a magnetism. A changing magnetic field produces an electric field. And when you follow that chain of logic through to its conclusion, something astonishing emerges. These two changing fields can sustain each other indefinitely, passing energy back and forth as they travel through empty space. Maxwell calculated the speed at which this self-sustaining ripple would travel. It came out to approximately 300 million meters per second, which was, already known, the speed of light. Light, Maxwell realized, is not something separate from electricity and magnetism. Light is electricity and magnetism. It is a wave in the electromagnetic field propagating through space. The warm glow of a candle, the heat of sunlight on your face, the faint signal from a distant radio tower, all of it is the same thing. All of it is one force, rippling. That was the second great unification. And then, at the turn of the 20th century, physics arrived at a threshold. Scientists had known for decades that matter was made of atoms, small, indivisible units, or so it was thought. But in 1909, a physicist named Ernest Rutherford, working in Manchester with his colleagues Hans Geiger and Ernest Marsden, performed an experiment that quietly changed everything. They took a thin sheet of gold foil, just a few atoms thick, and aimed a beam of tiny, positively charged particles at it. The particles were called alpha particles, and they were known to be fairly heavy, fairly energetic little things. The expectation was that they would pass through the foil with minor deflections, the way a bullet might pass through a thin sheet of paper, perhaps bending very slightly as it went. Most of them did exactly that, but some of them, a small fraction, bounced back, not bent slightly, bounced almost directly backward, as if they had struck something very hard and very dense. Rutherford later said it was as if you had fired artillery shells at tissue paper and they had bounced back and hit you. The result was so unexpected that it took him months to accept what it meant. What it meant was this: the atom is not a solid, uniform thing. Almost all of the atom's mass is concentrated in a tiny, incredibly dense region at the center, a nucleus, Rutherford called it, and the rest of the atom is essentially empty space. The electrons, which carry negative charge, orbit this nucleus at vast distances relative to the nucleus's size. If the nucleus of an atom were the size of a marble placed at the center of a football stadium, the electrons would be somewhere in the upper tiers of the stands. Everything in between is empty. This raised an immediate and urgent question. A nucleus contains protons, positively charged particles, and positive charges repel each other powerfully. So what is holding the nucleus together? Why don't all the protons in every nucleus in the universe immediately fly apart from each other, blown apart by their mutual electromagnetic repulsion? The answer could not be gravity. Gravity between particles that small is negligibly weak. The answer could not be electromagnetism. Electromagnetism was the very thing trying to tear the nucleus apart. There had to be something else, something stronger, something that operated only at very close range, binding protons and neutrons together in spite of the electromagnetic repulsion, keeping every nucleus in the universe intact. That something had no name yet. It was simply a gap in the picture, a silence where a new rule was waiting to be discovered. And sitting quietly alongside it was another gap. Radioactivity had been known since the 1890s. Certain atoms, left alone, would spontaneously transform into different atoms, releasing energy in the process. The mechanism was completely unknown. No one could explain why a neutron, sitting inside a nucleus, might suddenly change into a proton. No known force could account for it. So as the 20th century began, the picture looked like this. Gravity was understood, in Newton's terms at least. Electromagnetism was understood beautifully in Maxwell's terms. And somewhere inside the atom, in the tiny, dense nucleus that Rutherford had just revealed, two more forces were waiting, unnamed, unexplained, patient as the dark. The universe was already simpler than it looked. It was about to become simpler still. Before we can talk properly about what the four forces are, it helps to understand what a force actually is, at the deepest level we have currently reached. Because the answer is stranger and more beautiful than the word force might suggest. In everyday experience, a force feels like a push or a pull. You press your hand against a wall and the wall pushes back. A magnet draws a piece of iron toward it. The earth pulls you downward. These all feel like direct, immediate actions, one thing reaching out and grabbing another. But that picture, as intuitive as it is, breaks down completely when you look closely enough. At the level of individual particles, forces don't work through direct contact or invisible threads. They work through something far more interesting. The idea is this: when two particles exert a force on each other, they do so by passing something between them. A third particle, a messenger particle, is emitted by one and absorbed by the other. The exchange of this messenger is the force. The force is not a property of the two particles alone. The force is the event of the exchange. There is an image that physicists sometimes use to build the intuition, and it goes like this. Imagine two ice skaters standing on a frozen pond facing each other. One of them throws a heavy ball to the other. As she throws it, she recoils backward. As he catches it, he is pushed backward too. The act of throwing and catching has pushed them apart. The exchange of the ball has produced a repulsive effect. Now, this image captures the repulsion between like charges, two positive charges pushing away from each other through the exchange of messenger particles. The image breaks down somewhat for attraction, which requires a more sophisticated version of the analogy, but the central idea holds. The force is the exchange, and the messenger particle is the mechanism. These messenger particles are called gauge bosons. Each of the four fundamental forces has its own gauge boson, or set of them, its own specific type of messenger. The framework that describes all of this mathematically is called quantum field theory. It is worth taking a moment to understand what quantum field theory actually says, because it represents a genuinely different way of thinking about what the world is made of. In quantum field theory, the most fundamental things in nature are not particles. They are fields. A field, in this context, is something that has a value at every point in space, like temperature, which can be measured at every location in a room, or like the ripples on the surface of water, which extend across the entire surface. In quantum field theory, there is an electron field that fills all of space. There is a quark field. There is a photon field. Every type of particle corresponds to its own field, and a particle is what you get when that field is disturbed, when a ripple runs through it. An electron is a ripple in the electron field. A photon is a ripple in the photon field. When two electrons repel each other electromagnetically, what is actually happening, in the language of quantum field theory, is that the ripple in one electron field is disturbing the photon field, which disturbs the other electron field. This is a profound shift in perspective. The field is the fundamental thing. The particle is the field's way of expressing itself, and the force is the conversation between fields, conducted through the exchange of their respective messengers. Now, one of the most important properties of a messenger particle is whether or not it has mass. This turns out to determine something crucial: the range of the force. The photon, the messenger of the electromagnetic force, has no mass at all. It travels at the speed of light, which is not a coincidence, but a consequence of its being massless. And because it is massless, there is no energy cost to producing a photon and sending it across space. A photon can travel from one side of the universe to the other without any energy penalty. This is why the electromagnetic force has infinite range. It reaches everywhere, weakening with distance but never cutting off entirely. Now consider what happens if a messenger particle has mass. Mass, in quantum mechanics, is directly related to energy. A massive particle requires energy simply to exist. This means that a force whose messenger has mass can only afford to send that messenger a very short distance before the energy required becomes prohibitive. The range of the force is inversely related to the mass of its messenger. The heavier the messenger, the shorter the reach. This is not just an abstract principle. It has direct, measurable consequences for the forces we are about to explore. The weak nuclear force, for instance, has messengers that are extraordinarily heavy, roughly 80 to 90 times the mass of a proton, and its range is accordingly tiny, far smaller than the nucleus of an atom. The strong force's messengers, the gluons, are massless, which would suggest an infinite range, except that the strong force has another, very different mechanism that confines it, as we will come to. Gravity's messenger, if it has one, would also be massless, which would explain gravity's infinite range. But no one has ever detected a graviton directly, and the theoretical difficulties in describing gravity through quantum field theory remain the deepest open problem in all of physics. There is one more idea worth holding gently as we move forward. Every force has a corresponding field. The electromagnetic force has the electromagnetic field. The strong force has what physicists call the gluon field, and so on. And in each case, the field is more fundamental than the force. The force is what you experience when you, as a particle, interact with the field. The field exists whether or not you are there to feel it. You are lying in a field right now, several of them overlapping, filling every cubic centimeter of the room around you. The electromagnetic field, the gravitational field, fields whose ripples built the atoms in your body, fields whose interactions hold those atoms together, fields that carry the electrical signals moving through your nervous system as you drift towards sleep. They are always there. They do not switch off. They are the quiet background of everything. The strong force has its field. The weak force has its field. Gravity has its field. Electromagnetism has its field. And between them, these four fields account for every interaction that has ever occurred in the observable universe. We will take each one in turn, slowly, starting with the one that is, by any measure, the most powerful thing in nature. If you could stand inside an atomic nucleus, which you cannot, for reasons we will come to, you would be in the most intense environment that physics knows. Not the heat of a star's core, not the pressure at the heart of a collapsing sun, but this, the space inside a proton, where the strong nuclear force operates at full strength, is a place where the rules of the world feel almost incomprehensibly tight. The strong nuclear force is the most powerful of the four fundamental interactions. It is, at the distances where it operates, roughly 100 times stronger than the electromagnetic force, and somewhere in the region of 100 trillion times stronger than gravity. These are numbers that don't really fit in the mind, so it helps to think about what the force is actually doing. Every atomic nucleus, in your body, in the air, in the rock beneath the ground, in the core of the sun, contains protons. Contains protons carry positive electric charge. Positive charges repel each other, and they repel each other powerfully, with a force that grows stronger as they get closer together. Inside a nucleus, protons are packed at distances of roughly 1 femtometer, 1/1,000,000th of a billionth of a meter, from each other. At that distance, the electromagnetic repulsion between them is enormous, and yet they stay together. Every proton in every nucleus in the universe is held in place against that repulsion by the strong force. Without the strong force, there would be no nuclei. Without nuclei, there would be no atoms. Without atoms, there would be nothing. No chemistry, no planets, no stars, no you lying here in the quiet dark. Talk. The strong force is the chain that makes matter possible. But to understand how it works, we need to go one layer deeper than the proton itself. For most of the 20th century, the proton and the neutron were thought to be fundamental, the smallest indivisible units inside the nucleus. Then, in the 1960s, two physicists working independently, Murray Gell-Mann and George Zweig, proposed something that initially seemed almost too strange to take seriously. The proton and neutron, they suggested, are not fundamental at all. They are each made of smaller particles bound tightly together. Gell-Mann called these smaller particles quarks, a word he borrowed from a line in James Joyce's Finnegan's Wake. A proton is made of 3 quarks, 2 quarks of a type called up and 1 quark of a type called down. A neutron is also made of 3 quarks, 1 up quark and 2 down quarks. The difference between a proton and a neutron is simply the arrangement of the quarks inside them. Now, quarks carry electric charge. Up quarks carry a positive charge of 2/3. Down quarks carry a negative charge of 1/3. And these fractions add up to give the proton its overall charge of +1 and the neutron its overall charge of 0. But quarks also carry a completely different kind of charge, a charge that has nothing to do with electricity. Physicists call it color charge, not because quarks are literally colored, but because the mathematics of the force that acts on this charge has a structure somewhat analogous to the way colors mix. There are 3 types of color charge, labeled red, green, and blue, and their combinations follow specific rules, in the same way that red, green, and blue light combine to make white. Every quark carries 1 color charge, and the strong force acts on color charge the way the electromagnetic force acts on electric charge. It pulls together opposite values and drives the dynamics of the whole system. The messenger particles of the strong force are called gluons. They are massless, like photons, and they are exchanged between quarks in the same way photons are exchanged between electrically charged particles. But gluons have a property that photons do not. Gluons themselves carry color charge. A photon is electrically neutral. It carries the electromagnetic interaction, but does not itself feel the electromagnetic force. A gluon, by contrast, does carry color charge, which means gluons interact with each other as well as with quarks. This self-interaction of the gluons is what makes the strong force so very different from electromagnetism, and it is the root of one of the strangest facts in all of physics. That strange fact is called color confinement. It is the observation, confirmed by decades of experiment, that no particle carrying a net color charge has ever been observed in isolation. Quarks are never found alone. Gluons are never found alone. They are always bound together in combinations whose color charges cancel out, producing what physicists call color. The reason for this confinement lies in how the strong force behaves with distance. When you pull 2 electrically charged particles apart, the electromagnetic force between them weakens. Pull them far enough apart and the force becomes negligible. You can separate them. It stays roughly constant or even grows stronger as the separation increases. The image that captures this is an elastic band. Stretch a rubber band between your fingers. The further you pull, the harder it pulls back. The strong force between quarks behaves similarly. The further apart the quarks get, the more the force resists. And because gluons interact with each other, the force between quarks is not transmitted through a diffuse field spreading in all directions the way gravity or electromagnetism does. Instead, it is channeled through a narrow tube of gluon field, a flux tube, physicists call it, stretched between the quarks like a taut string. Now, what happens when you pull hard enough? When you pour enough energy into stretching that flux tube? The answer is extraordinary. At some point, the energy stored in the tube becomes large enough that it is more energetically favorable for the universe to create a new pair of quarks, a quark and its antimatter counterpart, an antiquark, right there in the middle of the tube, rather than to allow the tube to stretch further. The tube snaps, and where there was one long tube, there are now two shorter ones, each with its own quark at each end. This is why you cannot pull a quark out of a proton and hold it in isolation. Every time you try, you simply create new quarks. The quarks are always confined, always paired or tripled into color, neutral combinations. A lone quark has never been seen, and according to our current understanding, never will be. The quarks inside a proton are in constant motion, not the slow, sedate orbit of an electron around a nucleus, but a frantic, high-energy dance. And here is something quietly astonishing about this. The quarks themselves are almost weightless. The up quark has a mass of only a few electron masses. The down quark is slightly heavier, but still negligible. 3 such quarks added together should produce a proton with a tiny fraction of the proton's actual measured mass. But the proton weighs almost 2,000 times more than an electron. So where does that mass come from? It comes from the energy of the gluon field, the energy stored in the flux tubes, the kinetic energy of the quarks as they move, the constant churning of the color field inside the proton. Mass and energy are equivalent, as Einstein showed, and the mass of a proton is almost entirely the energy of its internal dynamics. The quarks themselves contribute only about 1% of the proton's mass. The rest is the strong force expressed as mass. Which means that when you hold your hand up and look at it, almost all of its mass, almost all of the mass of every proton and neutron in every atom in your body, is not the mass of any material thing at all. It is the frozen energy of the strong force confined inside tiny spheres of gluon field vibrating in the dark. Now, the strong force that binds quarks inside protons and neutrons operates at a scale far smaller than the nucleus itself. But the nucleus contains many protons and neutrons, and they need to be held together too. This is done by what physicists call the residual strong force, a kind of echo or spillover of the color force that operates between whole protons and neutrons. The mechanism works like this. Inside each proton and neutron, the gluon field is technically confined. The color charges cancel out, and the particle is color neutral overall. But at very short distances, the cancellation is not perfect. The color fields from the quarks inside one proton can reach slightly outside the proton's boundary and interact with the quarks inside a neighboring proton or neutron. It is a faint residual effect, like the way two neutral magnets can still interact slightly through their internal structure. This residual strong force is mediated not by individual gluons, but by composite particles called pions, particles made of a quark and an antiquark bound together. Hideki Yukawa predicted their existence in 1935, before they were discovered, by reasoning from the known range of the nuclear force backward to the mass the messenger particle would need to have. His prediction was confirmed in 1947. The residual strong force has a very short range, only a few femtometers, roughly the diameter of the nucleus itself. Beyond that distance, it falls off rapidly. This is why nuclei have a maximum practical size. Beyond a certain number of protons and neutrons, the nucleus becomes so large that protons on opposite sides can no longer feel the residual strong force between them, and the electromagnetic repulsion, which reaches further, begins to win. This is why very heavy elements, like uranium, are unstable. Their nuclei are on the edge of what the residual strong force can hold together. Every stable nucleus in the universe, every atom of carbon, oxygen, iron, calcium in your bones is held together by this residual echo of the color force. The strong force is the reason matter exists, and it does its work silently, invisibly, at scales far too small to see, in every atom everywhere. Of the four fundamental forces, the weak nuclear force is in many ways the most peculiar. It is not the strongest, nor the most familiar, nor does it hold anything together in any obvious way. It operates at the shortest range of any force, a range so tiny that it makes the nucleus of an atom look spacious by comparison, and it is, in ordinary everyday experience, almost entirely invisible. And yet without the weak force, the sun would not shine. Without the weak force, most of the elements heavier than iron would not exist. Without the weak force, the universe as we know it, with its chemistry, its planets, its biology, would be impossible. What makes the weak force unique is the one thing none of the other forces can do. The weak force can change the identity of a particle. It can transform one type of quark into another. In doing so, it can turn a neutron into a proton, or a proton into a neutron, releasing energy and producing new particles in the process. This transformation, this alchemy at the level of individual quarks, is called beta decay, and it is worth following through in careful detail because the mechanism is genuinely beautiful. Begin with a neutron. A neutron, as we established in the previous chapter, is made of 3 quarks, 1 up quark and 2 down quarks. It carries no electric charge. The charges of its quarks cancel out exactly. A proton, by contrast, contains 2 up quarks and 1 down quark and carries a net positive charge. Now, under certain conditions, particularly when a nucleus has too many neutrons relative to its protons to be stable, something happens inside the neutron. One of its down quarks undergoes a change. It emits a messenger particle called the W boson, specifically the negatively charged version, the W- boson, and in doing so, flips its identity from a down quark to an up quark. Think about what this means. The neutron had 1 up quark and 2 down quarks. Now, with one of those down quarks having become an up quark, it has 2 up quarks and 1 down quark. It is no longer a neutron. It has become a proton. The W- boson that was emitted in this process is extremely heavy, about 85 times the mass of a proton, and it exists for an extraordinarily brief time, far too short to ever be observed in flight. Almost instantly, it decays into 2 lighter particles, an electron and a particle called an electron antineutrino. The electron flies away from the nucleus, and this is what we detect as beta radiation. The beta particle in beta decay is simply this electron, produced by the transformation of a quark inside a neutron. The antineutrino is something else entirely. It is a ghost-like particle with almost no mass. For a long time it was believed to have exactly 0 mass, though we now know it has a tiny but non-zero mass, and it carries no electric charge. It interacts with ordinary matter only through the weak force and through gravity, both of which are either very short range or very weak at the scales involved. This means a neutrino can travel through matter almost as if it weren't there. Every second, approximately 65 billion neutrinos from the sun pass through every square centimeter of your body, through your skin, through your organs, through the mattress beneath you, through the planet itself. You feel nothing. They pass through as if everything solid were empty air. The W- boson is one of 3 messenger particles of the weak force. The other 2 are the W+ boson, the mirror image of the W-, carrying positive charge, and the Z boson, which is electrically neutral. These 3 particles were predicted theoretically in the 1960s and 70s and discovered experimentally at CERN in 1983 in one of the great experimental triumphs of 20th century physics. Their discovery confirmed the electroweak theory, which we will come to in a later chapter. The enormous mass of the W and Z bosons, around 80 to 90 times the mass of a proton, is the direct reason the weak force has such a short range. Recall the principle from the previous chapter. The heavier the messenger, the shorter the reach of the force. The W and Z bosons are so heavy that the weak force can only carry its influence across a distance of about 1,000th of a femtometer, 1,000 times smaller than a proton. At distances any larger than that, the weak force is effectively zero. This is why it is called weak, not because the underlying interaction is feeble in itself, but because at the distances between particles in everyday matter, it is so short-ranged as to be almost negligible, to within that 1,000th of a femtometer range, and the weak force can act powerfully. But in practice, that proximity is extremely rare. Now, why does any of this matter at cosmic scales? Why should the fact that a down quark can occasionally flip into an up quark be relevant to the burning of stars? The answer lies in the fusion chain that powers the sun. The sun shines by fusing hydrogen, the lightest element, whose nucleus is a single proton, into helium, whose nucleus contains 2 protons and 2 neutrons. But here is the problem. 2 protons alone cannot form a stable nucleus. A nucleus of 2 protons, no neutrons, is not a stable configuration. You need neutrons in there for the strong force to hold everything together against the electromagnetic repulsion. So for hydrogen to fuse into helium, somewhere in the process a proton must become a neutron. And for a proton to become a neutron, one of its up quarks must flip into a down quark. And the only force that can do this is the weak force. The first step in the sun's fusion chain is the collision of 2 protons to form a particle called a deuteron, a nucleus containing 1 proton and 1 neutron, plus a positron and a neutrino. In this step, one of the protons has been converted into a neutron by the weak force. Without this step, the chain cannot proceed. Without the weak force, the sun's fusion could not begin. And because the weak force is so feeble at the relevant scales, this first step is extraordinarily slow. A typical proton in the core of the sun will wait, on average, around 9 billion years before it undergoes this reaction. 9 billion years. The sun is only about 4.5 billion years old, which means the average proton at the sun's core has not yet had its turn. The sun burns slowly precisely because the weak force is so reluctant to act. This slowness is, in a deep sense, a gift. It is why the sun has shone steadily for billions of years rather than burning out in a geological eye blink, and it is part of why life on Earth had the time to evolve. The weak force also plays a central role in the deaths of massive stars and the creation of the elements. When a star many times the mass of the sun exhausts its nuclear fuel, its core collapses under gravity in a fraction of a second. The collapse is so rapid and so dense that the core reaches temperatures and pressures where protons and electrons are forced together, combining through the weak force to form neutrons and neutrinos. The neutrinos, produced in extraordinary numbers, roughly 10 to the power of 58 of them in a single second during a supernova, carry away most of the gravitational energy of the collapse. As they stream outward through the star's outer layers, they deposit enough energy to drive the explosion, the supernova. It is in these explosions and in the collisions of neutron stars that the elements heavier than iron are forged. Gold, silver, platinum, uranium, all of it built in the intense neutron-rich environments of stellar death, where the weak force drives the rapid transformation of protons and neutrons, building up heavier and heavier nuclei in a chain of reactions called the R. The gold in any jewelry you might own was forged in an event like this billions of years ago and scattered through space before the solar system formed. The weak force is quiet. It operates in places too small to see, at timescales that range from billionths of a second to billions of years. But it is the force of transformation. It is the reason the sun burns at the right pace. It is the reason the elements exist. It is the reason that the matter scattered by dying stars eventually found its way into planets and into the atoms of living things and into you, resting here in the dark. Of the four fundamental forces, electromagnetism is the one you live inside. It is not the most powerful. The strong force holds that title. And it is not the most mysterious. But it is the one that shapes almost every aspect of the world as you experience it, from the light falling on your eyelids to the warmth of a blanket to the signals moving through your nervous system right now. The messenger of the electromagnetic force is the photon. You already know the photon as the particle of light, the smallest possible packet of electromagnetic energy, indivisible, traveling always at the same speed through empty space. But the photon does far more than carry visible light. Every interaction between electrically charged particles, every attraction, every repulsion, every bond between atoms is mediated by the exchange of photons. Most of these photons are what physicists call virtual photons. They exist only as brief, transient messengers, never detected directly, never traveling far enough to be seen as light. They are the quiet carriers of every electromagnetic force. The photon has no mass. This is the reason the electromagnetic force has infinite range. A photon costs nothing to produce in the sense that no energy penalty is imposed for creating one and sending it across any distance. The force weakens with the square of the distance, double the distance, and the force drops to a quarter of its original strength, but it never cuts off. It reaches everywhere. Every charged particle in the universe is, in principle, feeling a tiny electromagnetic tug from every other charged particle in the universe, however faint. Now, the electromagnetic force acts on electric charge. There are two types of electric charge, positive and negative, and the rule is simple. Opposite charges attract, like charges repel. Protons carry positive charge, electrons carry negative charge, and the attraction between them is what holds every atom together. Consider a single hydrogen atom, one proton at the center, one electron, somewhere in the space around it. The electromagnetic attraction between them is what keeps the electron from flying away. But quantum mechanics tells us that the electron does not orbit the proton the way a planet orbits a star. It exists in a kind of smeared-out cloud, a probability distribution more likely to be found in some places than others, but not pinned to any particular location. The shape of this cloud, these probability distributions, called orbitals, is determined by the interplay of the electron's energy and the electromagnetic attraction pulling it toward the nucleus. When atoms combine to form molecules, it is again the electromagnetic force doing all the work. There are two main ways this happens. In one type of bond, an electron is transferred from one atom to another. The atom that loses the electron becomes positively charged. The atom that gains it becomes negatively charged, and the opposite charges attract, holding the atoms together. This is what happens in table salt, where sodium gives an electron to chlorine. In another type of bond, electrons are shared between atoms rather than transferred. They occupy orbitals that span both atoms simultaneously, and the shared electron cloud pulls both nuclei inward toward the shared space. This is what holds together the molecules of water, of proteins, of DNA. Every chemical bond, every molecule, every protein folded into its precise three-dimensional shape, every strand of DNA coiled in the nucleus of every cell, all of it is electromagnetic interaction mediated by the exchange of photons between electrons and protons, playing out at distances of a few angstroms, a few 10 billionths of a meter. This means that chemistry, all of chemistry, from the simplest reaction to the most complex biochemical cascade, is applied electromagnetism. The periodic table of elements, with its patterns of reactivity and bonding, is a map of how different configurations of electrons interact electromagnetically with each other. The fact that water is liquid at room temperature, the fact that carbon can form 4 bonds and build the complex scaffolding of organic molecules, the fact that oxygen is reactive and nitrogen is not. All of this follows from the electromagnetic force and the quantum rules governing how electrons occupy the space around nuclei. And then there is solidity. But electrons repel each other. They carry the same negative charge, and the Pauli exclusion principle, a rule from quantum mechanics stating that no two electrons can occupy exactly the same quantum state at the same time, means that the overlapping electron clouds cannot simply merge. The electrons resist, and the resistance is felt as a force pushing the two atoms apart. The solidity of matter is not a mechanical property, not something arising from atoms being like tiny billiard balls that physically block each other. It is electromagnetic repulsion. The floor beneath you is solid because the electrons in its atoms are pushing back against the electrons in your body's atoms, and the electromagnetic force is strong enough to hold you up against gravity. If you could somehow turn off the electromagnetic force, matter would not be solid at all. You would pass through everything. Every texture you have ever felt, every surface that has ever felt firm or soft or rough or smooth, every time you've picked something up or leaned against a wall or felt the weight of a blanket, that sensation is electromagnetic repulsion transmitted through the atoms of your skin. Now, the electromagnetic force is not just about static charges. Moving charges produce a different effect, magnetism. This was the great insight of the 19th century, the one that led Maxwell to his unification. A charge moving through space, an electric current flowing through a wire, or an electron orbiting a nucleus creates a magnetic field around it. And a changing magnetic field, in turn, creates an electric field. The two are inseparable. They are not two forces but one force, seen from different perspectives. Maxwell showed that this interplay between changing electric and changing magnetic fields produces something remarkable. If you set up a situation where an electric field is changing, oscillating back and forth, it generates a changing magnetic field, which generates a changing electric field, which generates a changing magnetic field, and so on. The oscillation propagates outward through space, carrying energy with it, sustaining itself through the mutual generation of each field from the other. This propagating oscillation is an electromagnetic wave. And the speed at which it propagates, which Maxwell calculated from the known properties of electricity and magnetism, is approximately 300 million meters per second, exactly the speed of light. Light is not illuminated by the electromagnetic force. Light is not carried by the electromagnetic force. Light is the electromagnetic force. It is the electromagnetic field oscillating and propagating through space. Visible light is electromagnetic waves with wavelengths between roughly 400 and 700 nanometers, a nanometer being a billionth of a metananometers, a nanometer being a billionth of a meter. Radio waves are electromagnetic waves with wavelengths of centimeters to kilometers. X-rays are electromagnetic waves with wavelengths far shorter than visible light, short enough to pass through soft tissue but be absorbed by denser bone. Gamma rays, microwaves, ultraviolet radiation, all of it is the same thing, electromagnetic waves at different frequencies. The warmth of sunlight on your skin, the signal reaching the radio antenna, the X-ray image of a broken bone, the faint glow of a distant star resolved by a telescope. All of it is the electromagnetic force, propagating through space in its waveform, arriving from somewhere else and interacting with charged particles when it arrives. There is something quietly moving about this, the light that falls on your closed eyelids right now. Whatever faint light there is in the room is the same phenomenon as the force that holds your atoms together. The electromagnetic force does not just enable your existence at the chemical level. It reaches outward from every charged particle in the universe, and its ripples, its waves, cross the cosmos, carrying information about distant fires, distant suns, the early universe itself. The electromagnetic force is the most present of the four. You are immersed in it, constituted by it, sustained by it. It is the medium through which you see and touch and are touched. Here is a comparison that is worth sitting with for a moment. Take a proton and an electron separated by a small distance. Between them, there is an electromagnetic attraction, the positive charge of the proton pulling on the negative charge of the electron, and there is also a gravitational attraction. Both are acting simultaneously. The ratio of the electromagnetic force to the gravitational force between these two particles is approximately 10 to the power of 36. That is a 1 followed by 36 zeros. The electromagnetic force is, in this comparison, 1,000,000,000,000,000,000,000,000,000,000,000,000 times stronger than gravity. To get a feel for what this means, if you scaled up the gravitational force between a proton and an electron until it was as strong as the electromagnetic force, you would need to make the proton as massive as a small moon. And yet gravity is the force that shapes the large-scale structure of the universe. Gravity is the force that gathered hydrogen gas into stars, that holds planets in their orbits, that bends light around massive objects, that will determine the ultimate fate of the cosmos. The answer has two parts. The first is range. Gravity, like electromagnetism, has infinite range. It weakens with distance but never reaches zero. A proton on one side of the galaxy is still, technically, feeling a gravitational pull from every other proton in the galaxy. The strong force and the weak force, by contrast, have ranges so short that beyond the nucleus they are effectively zero. So at any distance larger than a few femtometers, only gravity and electromagnetism are relevant. The second part of the answer is more subtle, and it is about cancellation. Electric charge comes in two types, positive and negative, and they cancel each other out. A hydrogen atom has one proton and one electron, and their charges cancel exactly. The atom is electrically neutral. A large object made of many atoms, a planet, a star, a galaxy, is, to an extraordinarily good approximation, electrically neutral overall. The positive and negative charges cancel, and the residual electromagnetic force between large neutral objects is negligible. Gravity has no such cancellation. Gravitational charge, mass, comes in only one type. There is no negative mass. Every kilogram of matter attracts every other kilogram of matter, always, with no cancellation possible. As you add more mass to an object, its gravitational pull increases monotonically. There is no way to screen it, no way to cancel it. And so, at the scale of planets and stars and galaxies, gravity accumulates without limit, while electromagnetism cancels to near zero, and gravity wins. The fridge magnet demonstrates this every morning. A small magnet, holding itself against the side of a refrigerator, is generating an electromagnetic force large enough to counteract the gravitational pull of the entire Earth on the magnet. This is how weak gravity is, even compared to a modest everyday magnet. Now, Newton's description of gravity as a force, a pull between masses, acting instantaneously across any distance, was extraordinarily successful for over 2 centuries. It predicted the motions of the planets to extraordinary precision. It explained tides, the paths of comets, the behavior of binary stars. But it had a conceptual problem. It offered no mechanism. How does the sun reach across 150 million kilometers of empty space and pull on the Earth? Newton himself acknowledged this, famously writing that he framed no hypotheses about the cause. The answer came from Albert Einstein in 1915 in the form of the general theory of relativity. Einstein's insight was that gravity is not a force in the conventional sense at all. It is a consequence of the geometry of space and time. The framework Einstein worked within, space-time, treats space and time not as separate things but as aspects of a single 4-dimensional fabric. Massive objects, Einstein proposed, do not send out a force that reaches across space. Instead, they curve space-time itself. The presence of mass and energy bends the fabric like a heavy ball resting on a stretched rubber sheet, creating a depression. Other objects moving through this curved space-time follow the curves. They take the paths that require the least energy, the natural paths through curved geometry, and we experience this as attraction, as gravity. The Earth follows a curved path around the Sun, not because the Sun is pulling it with an invisible thread, but because the Sun's mass has curved the space-time around it, and the Earth is following the straightest possible path through that curved geometry. From the Earth's perspective, it is moving in a straight line through curved space. From our perspective, looking at it from the outside, it traces an ellipse. This picture makes predictions that Newton's law cannot. It predicts that light, which has energy and therefore curves space-time slightly, will itself be bent by gravity. And this was confirmed during a solar eclipse in 1909, when stars near the Sun appeared slightly displaced because their light had curved around the Sun's gravitational field. It predicts that time runs more slowly in stronger gravitational fields, and this is not just a theoretical curiosity. The GPS satellites orbiting Earth experience slightly weaker gravity than we do on the surface, and their clocks run slightly faster as a result. The GPS system must correct for this difference constantly, or the position errors would accumulate to kilometers within a day. It also predicts gravitational waves, ripples in the fabric of space-time itself, propagating outward from accelerating masses the way electromagnetic waves propagate from accelerating charges. These were detected for the first time in 2015 by the LIGO experiment in the United States, when two black holes merging over 1 billion light-years away sent a ripple through space-time that stretched and compressed the detectors by a distance smaller than 1,000th of the diameter of a proton. That detection was one of the most precise measurements in the history of science. But Einstein's description of gravity, for all its elegance, is a classical theory. It describes space-time as smooth and continuous, without any of the granular, probabilistic structure of quantum mechanics. And at very small scales, or in very extreme conditions, inside a black hole, in the first instance after the Big Bang, the two theories are both relevant simultaneously, and they produce results that contradict each other. If gravity behaves like the other three forces at the quantum level, it should be mediated by a messenger particle. This hypothetical particle is called the graviton. It would be massless, consistent with gravity's infinite range, and it would have a spin of 2, a quantum mechanical property that distinguishes it from all the other force-carrying particles. Massless particles with spin 2 produce an attractive force for all masses, which is consistent with what we observe. But no one has ever detected a graviton. The gravitational force is so weak that the probability of a graviton interacting with any detector we could build is essentially 0. Even a detector the size of Jupiter, left running for the lifetime of the universe, would be unlikely to register a single graviton. And beyond the detection problem, there is a theoretical one. Attempts to build a quantum theory of gravity using the same methods that work for the other three forces produce mathematical results that are infinite and meaningless, resistant to the renormalization techniques. Gravity remains alone, the one force that does not fit inside the framework that describes the other three. The one force that is not yet reconciled with quantum mechanics. It is the deepest open question in physics, not whether there is a quantum theory of gravity, but what it looks like and where it will lead. And yet, gravity is the force that built the world. Every planet, every star, every galaxy cluster, assembled by the patient, unhurried accumulation of the weakest force in nature, acting over billions of years, pulling dust into clouds, clouds into stars, stars into galaxies, galaxies into the vast filamentary structure of the cosmos. Physics has always had a dream, not just to understand the forces, but to find out whether they are truly separate, or whether they are, at some deeper level, one. The first hint that this dream was achievable came from Maxwell's unification of electricity and magnetism in the 1860s. What had appeared to be two distinct forces turned out to be two aspects of one. The first answer came in the 1960s and 70s, and it concerned two forces that, on the surface, seemed to have almost nothing in common: electromagnetism and the weak nuclear force. Electromagnetism has infinite range and mediates interactions between charged particles through the massless photon. The weak force has a range 1,000 times smaller than a proton and mediates its interactions through the enormously heavy W and Z bosons. They seem completely different in character. And yet, three physicists, Sheldon Glashow, Abdus Salam, and Steven Weinberg, showed, through careful and painstaking theoretical work, that these two forces are in fact the same interaction, viewed under different conditions. At the energies typical of everyday physics, the energies of atoms, of chemical reactions, of the world we inhabit, they appear distinct. But at very high energies, energies far beyond anything achievable in ordinary circumstances, the two forces merge into a single interaction. They are unified into what is called the electroweak force. To understand why they look so different at low energies, you need to understand something about the Higgs field. The Higgs field is something distinct from the four forces. It is not itself a force carrier, but it is intimately related to why the forces have the properties they do. It is a field that fills all of space, everywhere, always. Unlike most fields, it does not point in any direction and does not oscillate around zero. It has a constant, non-zero value everywhere in the universe, the way the surface of the sea has a certain level, even in calm conditions. Particles moving through the Higgs field interact with it, and this interaction is what gives them mass. The more strongly a particle interacts with the Higgs field, the more mass it acquires. Particles that do not interact with the Higgs field at all, like the photon, remain massless. Here is the crucial point. The messengers of the electroweak force in the unified theory are all initially massless, 4 of them, labeled by their mathematical properties. In a universe where the Higgs field was zero everywhere, all 4 would remain massless. The electroweak force would have infinite range in all its aspects, and electromagnetism and the weak force would be indistinguishable. But the Higgs field is not zero. It has that constant non-zero value everywhere. And when 3 of the 4 electroweak messenger particles interact with the Higgs field, they acquire mass, large mass, the mass of the W+, W-, and Z bosons. The 4th messenger particle does not interact with the Higgs field and remains massless. That is the photon. The symmetry between the 4 messengers is broken by the Higgs field, and what was one unified force splits into 2, the short-range massive messenger weak force and the infinite-range, massless, messenger electromagnetic force. This breaking of symmetry by the Higgs field, physicists call it spontaneous symmetry breaking, meaning the underlying physics is symmetric, but the actual state of the universe is not, is the mechanism that makes the weak force weak at low energies. The W and Z bosons are heavy not because the weak force is inherently different from electromagnetism, but because they are swimming through the Higgs field and acquiring mass from it. The ripple in the Higgs field, the particle associated with disturbances in the field, in the same way that the photon is the particle associated with disturbances in the electromagnetic field, is the Higgs boson. Its existence was predicted by the theory decades before it was found. And in 2012, after nearly 50 years of searching, physicists at CERN announced its discovery, detected in the collisions of protons in the Large Hadron Collider. The Higgs boson had a mass of approximately 125 times the mass of a proton, in the range the theory had suggested was plausible, and its properties matched the predictions of the electroweak theory with striking precision. The discovery of the Higgs boson completed the standard model, the theoretical framework that describes electromagnetism, the weak force and the strong force, along with all the matter particles they act upon. The Standard Model is, by any measure, one of the most successful theories in the history of science. Its predictions have been tested to extraordinary precision, in some cases agreeing with experiment to better than 1 part in a billion. The next step in the unification project, combining the electroweak force with the strong force into a single interaction, is called grand unification. Theories that attempt this exist, and they make predictions. Among other things, they predict that the proton itself is not stable, but will eventually decay, on a timescale so long that no proton has ever been observed to decay in any experiment. The current experimental lower limit on the proton's lifetime is around 10 to the power of 34 years, a number so vast that the universe's current age of about 14 billion years is negligible by comparison. Experiments continue to watch for proton decay. None has been seen. Grand unification remains unconfirmed. And then there is the frontier, the place where the Standard Model's precision runs up against something it cannot explain. The muon is a particle very much like the electron. It carries the same charge, it interacts via the same forces, and it behaves in most respects like a heavier version of the electron, about 200 times heavier, to be specific. One of the properties a particle like the muon has is a magnetic moment, a measure of how strongly it acts like a tiny magnet, arising from its spin and its charge. The Standard Model predicts this magnetic moment with extraordinary precision, accounting for all the virtual particles and interactions that contribute to it. But the measured value of the muon's magnetic moment does not quite match the prediction. The discrepancy is tiny, a difference in the last few decimal places of the measurement, but it is persistent, and it has been accumulating across multiple experiments over more than 2 decades. The muon G2 experiment at Fermilab in Illinois, where G2 refers to the specific way the magnetic moment is measured as a deviation from a baseline value, has been taking data for several years, measuring the muon's magnetic moment with extraordinary precision. The final result, based on 6 years of accumulated data and published in 2025, achieved a precision of 127 parts per billion, the most precise measurement of this quantity ever made, and it confirmed the discrepancy with the Standard Model's prediction that earlier results had suggested. The significance of the disagreement, combining Fermilab's data with earlier results from the Brookhaven National Laboratory, sits at around 4.2 sigma, a statistical measure of how unlikely the discrepancy is to be a random fluctuation. In particle physics, a discrepancy of 5 sigma is traditionally required before a finding is called a discovery. 4.2 sigma is just below that threshold, but it is not a small signal. It is a persistent, carefully measured disagreement that has survived increasingly precise experiments. What could be causing it? The honest answer is that no one is certain. The most natural explanation is that there is some particle or interaction not included in the Standard Model, something that interacts with the muon and shifts its magnetic moment slightly. It could be a new, as yet undiscovered particle. It could be an undiscovered force, a fifth fundamental interaction. It could be a modification to the Standard Model's predictions that arises from very subtle theoretical calculations that are still being refined. There is also a complication on the theoretical side. The Standard Model's prediction of the muon's magnetic moment involves extremely involved calculations, particularly the contribution from the strong force, which is notoriously difficult to compute precisely. In recent years, new theoretical calculations using different methods, including large-scale computer simulations of the strong force, have produced values that are in better agreement with the experiment, reducing the apparent discrepancy. This has created an interesting situation in which the experimental result and the theoretical prediction are both under active refinement, and the true size of the disagreement is itself somewhat uncertain. But the possibility remains, and it is taken seriously by many physicists, that the muon is feeling something the Standard Model does not account for. That something is nudging it, gently, in ways the current theory cannot explain, It is a quiet signal at the edge of what we know. The history of physics suggests that such quiet signals, when they are real, lead somewhere profound. We have come a long way tonight, from ancient lodestones and falling apples, through the interior of the proton and the slow alchemy of stellar fusion, to the edges of what physics currently knows. And now, in this last and slowest chapter, we can set aside the mechanism and sit with the meaning. 4 forces, just 4. The strong force, the weak force, electromagnetism, and gravity. Between them, they account for every interaction that has ever occurred in the observable universe, every collision of particles in the first moments after the Big Bang, every nuclear reaction in every star that has ever burned, every chemical bond that has ever formed, every photon that has ever crossed the cosmos, every tide, every heartbeat, every thought. All of it is one or more of these 4 interactions, playing out across 13.8 billion years of cosmic history. Sit with the strong force for a moment. It is the force you never feel directly, the force that operates at distances too small to imagine, binding quarks into protons and neutrons through the exchange of gluons, confining color charge so absolutely that no lone quark has ever been seen. It is the force whose residual echo, transmitted through pions, holds protons and neutrons together inside every nucleus in the universe. Without it, there are no nuclei. Without nuclei, there are no atoms. Without atoms, there is nothing, no chemistry, no matter, no world. The strong force is the precondition for everything else. It is the chain that makes substance possible. And yet it is entirely invisible in daily life. You will never feel it. You will never notice it. It works in the dark, at scales 100,000 times smaller than an atom, and it has been working without interruption since the first protons and neutrons formed, a tiny fraction of a second after the universe began. The atoms of calcium in your bones were forged in the cores of stars that died before the solar system existed. The carbon in your cells was assembled in stellar interiors where temperatures reached tens of millions of degrees. The oxygen you breathe was scattered through space by supernova explosions. All of those atoms in all of those stars were held together, nucleus by nucleus, proton by proton, by the strong force. Every atom in your body is a monument to it. The weak force is the quietest of the 4, the most hidden, the most easily overlooked. But it is the force of transformation, the force that keeps the universe moving forward. Without it, a proton could never become a neutron. Without that transformation, the fusion chain in the sun's core could not proceed. The sun would not shine. The earth would be dark and frozen. The chemistry of life would be impossible. The weak force is also the force that, in the deaths of massive stars, drives the supernova explosion and scatters the newly forged elements through the galaxy. The gold in the ground, the iodine in your thyroid, the zinc in your cells, all of it was scattered by processes driven by the weak force in the deaths of stars that lived and died long before our sun was born. The weak force is patient. A proton in the sun's core waits, on average, billions of years for the weak force to act on it. The sun has been burning for 4.5 billion years on the strength of this patience. The weak force's slowness is the reason the sun will continue to shine for another 5 billion years or so, long enough, in the grand sweep of things, for life to have arisen and wondered about it. Electromagnetism is the force you live inside. It is the force that holds every atom together, that builds every molecule, that drives every chemical reaction in your body. The proteins folding inside your cells right now, if you are still awake enough to have cells doing anything complicated, are held in their shapes by electromagnetic interactions between their constituent atoms. Charge flow. The warmth of the room around you, however faint, is infrared radiation. electromagnetic waves emitted by every warm surface. And electromagnetism is the force whose waves carry information across the cosmos. The light from the most distant galaxies we can observe has been traveling for over 13 billion years, and it arrives as electromagnetic radiation, as photons, massless messengers of the electromagnetic field, carrying information about stars and galaxies that formed when the universe was young. Every telescope in the world is an electromagnetic receiver. Every image of the cosmos is a portrait of the electromagnetic force propagating through space. The force that holds your atoms together is the same force that carries starlight. The interaction that makes your skin feel solid to the touch is the same interaction that makes radio waves. Electricity, magnetism, light, one thing, three names. And then gravity, the weakest of the four, weaker than electromagnetism by a factor so large that no ordinary language can convey it. And yet the force that, at the scale of the universe, is responsible for everything large. Gravity gathered the hydrogen gas produced in the Big Bang into clouds. Those clouds collapsed under their own weight, and at their centers the pressure and temperature became high enough for nuclear fusion to begin, for the strong force and the weak force to take over, building heavier elements from hydrogen. Stars were born. They lived for millions or billions of years, burning through their fuel, and then they died. Some quietly, some explosively, scattering their material into the surrounding space. Gravity gathered that enriched gas into new clouds, new stars, and this time the leftover material that did not fall into the star condensed into disks, and from those disks planets formed. The Earth exists because of gravity. Life exists on Earth because gravity held the planet together, held the atmosphere in place, kept liquid water on the surface, and the sun, whose light and warmth made photosynthesis and the whole chain of life possible, exists because gravity compressed hydrogen gas until the strong and weak forces could ignite it. Gravity is the architect. It draws the large-scale blueprint of the universe, assembling the stage on which the other three forces play out their intricate dramas. Three of the four forces, the strong, the weak, and electromagnetism, are now described within a single mathematical framework called the Standard Model of Particle Physics. This framework, developed through the 1960s and 70s and confirmed through decades of experiment, describes how quarks and leptons, the fundamental matter, particles. It is not a complete theory of everything, but it is the most precisely tested theory in the history of science. Its predictions have been confirmed again and again to extraordinary accuracy in experiments around the world. Gravity stands apart. Einstein's general theory of relativity describes gravity beautifully at the large scales where it dominates, but it is a classical theory. It does not incorporate quantum mechanics, and the two frameworks, quantum field theory and general relativity, are inconsistent with each other when both are relevant simultaneously. The reconciliation of gravity with quantum mechanics, the construction of a theory of quantum gravity, remains the deepest unsolved problem in all of physics. String theory, loop quantum gravity, and other approaches have been proposed, but none has yet produced testable predictions that experiments have confirmed. The universe, for now, runs on four forces, three of which we understand quite well, and one of which we understand only partially. It is an asymmetry that sits at the heart of modern physics, a gap that researchers spend their careers trying to close. And yet, even incomplete, the picture is extraordinary. Four interactions. That is all. The entire observable universe, in all its richness and variety, is the expression of four rules. There is something worth sitting with in this. The fact that the world is not arbitrary, that it is not governed by an infinite number of separate rules, one for every phenomenon, suggests something about the deep structure of reality. It suggests that beneath the apparent complexity of things, there is simplicity. Not the simplicity of emptiness, but the simplicity of depth, a few rules applied everywhere, generating everything. And now, as this night deepens and the words begin to arrive more slowly, there is one last image to carry with you towards sleep. The brain, as it moves through the stages of sleep, generates electrical rhythms, waves of coordinated activity that sweep across millions of neurons simultaneously. In deep sleep, these are slow and vast, the delta waves rolling through the cortex at frequencies of 1 to 4 cycles per second, each wave representing the synchronized firing of enormous populations of cells. In lighter sleep, the waves are faster, smaller, more varied. In dreaming, they become almost indistinguishable from waking. These rhythms, the electrical signature of the sleeping brain, are electromagnetic. The signals that pass between neurons, the electrical potentials that sweep along nerve fibers, the chemical signals that cross the tiny gaps between one neuron and the next, all of it is electromagnetic interaction. Charged ions moving across membranes driven by electromagnetic gradients. Photons, virtual photons, the mediators of the electromagnetic force, exchange between molecules at synapses, binding to receptors, triggering cascades of charge movement. The same force that carries light across the cosmos is, right now, carrying the signals of your dreaming mind. The same interaction that holds every atom of your body together is the one sustaining the slow electrical tide of deep sleep. And the atoms themselves, each one a nucleus held together by the strong force, surrounded by electrons bound by electromagnetism, assembled from elements forged in stars by the weak force, gathered into a world by gravity, are, in this moment, at rest. Not truly still. The quarks inside every proton are still moving, the electrons still occupying their probability clouds, the gluons still being exchanged, but resting in their configurations, stable, patient, as they have been for billions of years. You are made of the oldest processes in the universe. The atoms in your body have been through stellar interiors, through the cold of interstellar space, through the chemistry of a young planet, through the long, slow work of evolution. They have been part of stars and dust and ocean and air and countless living things before they were part of you, and they are held together right now by the same four forces that have governed every arrangement of matter since the beginning of time. The strong force holds your nuclei. The weak force once forged the elements that make you. Electromagnetism holds your atoms, your molecules, your cells, and carries the quiet electrical murmur of your resting brain. Gravity holds you gently against the earth, keeps the air around you, keeps the sun in its place. All fall, all at once, all the time, silent, patient, ancient. And so we leave it there. The day is already somewhere far behind you, distant as a dream you have half forgotten. The forces are still doing their work, as they always have. The atoms are quiet. The brain is slowing. Drift now, if you are ready.